All right. Okay. So up until now, what we have studied is what graduation is. Maybe not precisely the method which we use to graduate, the mortality rate, but we have seen, what can we do once we graduate the rates and what is the purpose of graduating the mortality rates. So the mortality rates that we observe, we call them crude ones, right? So those are not smooth and they might have some sort of variance, sampling variance, and to just even out all of these little errors that we have and to make our life easier as someone who will use this mortality rates to price something else. So if I'm a life insurance company, I do care about, the mortality rates being smooth because I cannot charge a higher premium and then a lower premium and then a higher premium if I'm considering a linear increase in the age, because then it might distort the people's incentive to come out and basically take a policy. So that shouldn't happen. And we expect the premiums to be smoothly progressing over the ages so that people do not find it advantageous to take insurance at one particular age compared to, let's say, another age. So, that could still be the case due to other factors, but it shouldn't be the case that because the way we have set the premium, there is a distortion. So at least from the premium point of view, we do not want there to be any such kind of a distortion. And this is just one of the reasons why we want to graduate the mortality rates. And once we graduate the mortality rates, the rates that we now have are known as the graduated mortality rates. So in the previous chapter, we studied various different kinds of tests that we can do to check whether the graduated rates that we have do correspond and imbibe the characteristics of the crude ones that we started off with. So we had some tests. We did group signs, cumulative deviations, chi-square simple, and we saw what is the lacuna in each of these tests. And we basically tried to figure out a perfect way to analyze what kind of a method should we use and what kind of a test should we use to check a particular feature of the data that we have fitted, right? So in this chapter, today we are going to have a look at the 3 different kind of ways we can actually graduate. So graduate, when I say 3 ways of graduating, seems like you can take science and graduate, you can take art and graduate, not that kind of graduate. So you can graduate mortality rates, right? That is the graduation that we're talking about. And again, I think, why do we have this word graduation, right? Because we want the mortality rates to be gradually, progressing. So be it increasing, decreasing, or increasing and then decreasing to specify some feature, let's say. So if we are talking about male population, we see there is a higher chance of some person being dead around their teenagers because they tend to drive hastily and they might just be careless. That is not that every male has that feature, but at least majority of them do have. So that is what has been observed, and it is known as the accident hum that you observe around those ages in men. So sometimes you might want to have, a graduate, smooth flowing mortality rates, and that is why it is known as graduation. So I guess that's it about this thing. Okay, so discussing the 3 methods, the very first method that we can use to graduate the rates is using a specific kind of a formula. So there are 3 different ways, 1, 2, 3, that we will be studying broadly. So one is using formula. And we can basically use Gompertz, Meckham's, Weibel's, or any other formula that you think might suit well. And we'll study each of these techniques in detail soon. And the second method is using a standard table. So sometimes what you have is, let's say if you are studying a particular niche of people who have taken insurance. So let us say if you're talking about the pensioners, or let's say if you're talking about the insurance, a particular kind of insurance for which you have a standard table already, then you can use this kind of technique where you graduate the mortality rate using a standard table. And the third kind of method that we will see is some splines. So let me just write it as polynomial. So some polynomial approximation. So again, here when I'm talking about a formula, this in itself is a polynomial approximation, but this is some specific kind of a polynomial approximation, which is known as splines. So I was trying to search what does this spline in general mean, and it is something I couldn't quite understand its meaning in terms of the mechanics. And I tried asking a couple of people, but they didn't seem to know anything about it. So I'll try to explain my best using just the statistics. So I was trying to find a way to, intuitively explain to you guys what does spline mean. But I guess we'll see how well I can do that. All right, so these are the three methods that we'll be studying. And again, apart from these three general methods, you can also go on to just, basically do it using your eye. Let us say if you do not want to use these graduated rates to forecast something in the future, all you can do is you can just graph the crude rates, and then we have already seen, right? You take the first difference, second difference, and the third difference. And the first difference will measure the slope. Second difference will measure the curvature of your curve. And the third difference will measure the rate of change of curvature. And what we want is that the rate of change of curvature should be very, very small, right? Because we do not want our mortality rates to be up and low, high and low, all every time. We want them to be gradually smoothing out. So, but that is only in the, this kind of a graphical method would not be suitable for every purpose. So, maybe one wrong assumption will alter the whole result for worse. And again, this is very subjective, because if you are trying to fit it just by hand, then it's subjective. Many people will try it and not everyone will get the same answer. So you don't know which one you should rely on. But again, here there is no unique or best solution. If you do not have a very specific purpose in mind of using these graduated rates, and you just want to see what is the main feature of this particular population that you're looking at, then you can have something, just a graph. You can have a look at the graph and just join the dots using, freehand technique or something like that. So if it's a small set of data, then you can use it. So that's fine. But that is just about maybe I can write it here. So fourth technique, which is graphical graduation. So again, this is just something like freehand. So let us say if you have something like this, if you observe, you can just try to just draw something like this. Yeah, something like that. It doesn't matter much. That's just an example. All right. So now let us try to see how do we proceed with we are going to discuss three methods, but whatever. Okay, so very first we would like to discuss about So we'll try to discuss about how do we graduate the mortality rates using a parametric formula. So the very first thing that we need to remember is that not every technique of graduation is suitable for any data set that we might have. So this particular technique, which is by using a parametric formula, is suitable only in the case where you have large set of data, because you would want this formula to fit perfectly, and basically you do not want to overgraduate and you do not want to undergraduate as well. So sometimes, again, just to revise, when I'm talking about undergraduation, what I might do is strictly adhere to the data crude rates, but I will get a rough graph. It will not be as smooth as I would want it to be. So there will be sudden bends, and yeah, it will just be rough in nature. And if and that would be the case of undergraduation. But on the other hand, if you try to smoothen it as nicely as possible, and while doing that, you do not adhere to the data as closely, or you lose out some of the feature of the data, then that will result in the case of overgraduation. So again, that might happen if we do not fit a perfect formula. So let us see, if you take too many parameters, in trying to fit the data as best as possible, then you might tend to undergraduate. Or if you take two less parameters, then you might tend to overgraduate. So again, how will we know whether we have overgraduated or undergraduated? We will have tests and also often we will try to use 2 or 3 different formulas. So we can try, let's say, with a very small formula, and then we'll try to add on something to it. We'll have a bunch of formulas nested into one another, and then we can check whether there is significant difference or is this particular parameter significant or not. So we have already started likelihood ratio test and other tests to check whether two models, which one of these models will provide you a better goodness of fit. And of course, you should go with the one which provides you the least, chi-square statistic or better goodness of fit in general, I would say. Okay, so again here they've given us the two simple formulas. Gompertz, we know that the modality rate, so here I'm using mu x. So again, ideally if I were looking at age next, then I would have written x plus half, but just assume that I'm considering age nearest, so that the central rate of mortality is mu of x. So if that is the case, then this is how my Gompertz formula looks like. And this is just another formula for Mayhem. So this is one additional parameter that we add, which is independent of the age. So there is something else that we think might happen or might influence the mortality rates. All right. So here they have just again said that because my mortality rate often resembles an exponential curve, at least in the middle and the lower ages, not in the younger ones, because of the fact that infant mortality rate, even if you go and check the census data, they will specifically, so whenever we go and try to even study mortality data, they will ask you, what kind of mortality data do you want to study? So there are different kinds. So sometimes you only want to study infant mortality data. Sometimes you want to study under 5-year-old mortality data. Sometimes you want to study prenatal mortality data. Sometimes you want to study the overall population's mortality data. So there are some unique features that we observe in the infant times and in the childhood period. So that does not adhere much to the exponential curve, but the middle and older ages do actually, adhere to the exponential curve. And they haven't given here, but this is much more good of an approximation in the case of developed countries. So yeah, that is, I guess. So the next thing that we studied is if we combine both of these formulas, right? So what we are trying to do here, yeah, no worries, Isha, no worries, Isha. That is what I told you previously, right? So do not worry, it's fine if you leave as well. It's theory, it's like mostly theory today and in the next lecture as well. Okay, so here what I was trying to say is that we're looking at this central rate of mortality, and instead of having only this or only this, we can have a combination, right? So why restrict this to only c raised to x? We can have other polynomials as well. So c raised to x plus x squared or something else if we want to, right? So we'll try to fit different kinds of formulas, and we will see which one of those fits the data that we have at hand the best, right? So here I'm looking at polynomial 1, which is something like this, if I'm considering a comparison between these two, and e raised to a certain polynomial 2. So e raised to a certain polynomial 2.
Ma'am,
You can rewrite.
I think you're
Yes, we hear. Yes, Mihir.
Ma'am, I think your screen has frozen.
Oh, you guys. Oh, okay. When did this happen? Can you guys see it now?
Yes, ma'am.
Was it like that, like up until now, or did it just happen? I just, even if it was, I think it just
Ma'am,
doesn't
but
seem
we
that.
understood it.
Okay, yeah, fine. All right. So what I was saying is this is the Gompertz formula and this is the Maychem's formula, right? And the another was the family, right? That we saw Gompertz-Maychem family. So you can derive a mortality rate using some polynomial and then e raised to some another polynomial. And you can see that Gompertz and Maychem individually are just special cases of this. So they have shown that here. So again, I mean, if you might see that there is no e raised to x here, ma'am, don't worry, you can put a log and put the e there, you will get e raised to blah, 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 whatever you want. So I think that you can do and see how it approximates to this particular family. But yeah, that is just one thing. Okay, so now we'll try to have a look at a practical example, which is not very practical, but yeah, just how do we fit a particular function? So if you remember, we have two parameters, one is r and one is s, which dictate the number of coefficients we have in total. So again, when I'm talking about the polynomial 1, we see that that polynomial is of a degree r. And when I'm talking about the second polynomial, polynomial 2, I see that polynomial is a polynomial of degree s. So what happens here is we have these many parameters, alpha 1 till alpha r plus s, and x, which represents the age, right? So this is everything that we expect our graduated mortality rate to depend on. So if you see here, now I have a circle up there, right? That represents the graduated rate. So I'm trying to fit my formula, and it will be some function of these parameters, which I expect to be equal to the graduated rate. So this is the formula that I'm trying to fit to figure out this particular term, right? So my polynomial 1, I define it as something like this. And polynomial 2, I define it as something like this. So here you don't see any x, and here you don't see any x. So just consider it as x raised to 0, which takes a value of 1. So that you get a nice progression of x being raised to 0, 1, 2, and up until r minus 1 here. And here you get up until s minus 1. So in total, if you see the number of coefficients that you have is r minus 1 plus 1, s minus 1 plus 1, which is nothing but r plus s. And that is what you have here. So again, these are the number of parameters, and yes, this is the formula that we will try to fit. But again, when it comes to figuring out this particular stuff, you can also try to use a specific formula. Let's say if we assume that the number of deaths that we observe, it follows, let's say, Poisson distribution. So you can choose to have a binomial distribution as well. And in that case, we know we won't be looking at central exposed to risk. And we'll be using QX and we'll use EX, right? Not C up there in the subscript, the superscript. So now let us say we're assuming that we have a Poisson model, and that is, I mean, the probability that you observe deaths, they follow Poisson model. So we can have something like this. So here, instead of writing dx, which is the random variable which denotes the number of deaths, we have used the formula that my mortality rate, which is mu x, is equal to dx upon exc. So if I rearrange it, I get that my dx is nothing but mu x times exc, which is what I have done here. And this is basically the mean and the variance as well. So if you see lambda, instead of lambda, we have written these particular things here. So you have e raised to minus lambda and lambda raised to x upon x factorial, right? And our x is dx now, and my lambda is exc times mu of x. So I guess once you have that, then you can actually try to figure out the parameters. And to figure out the parameters, again, always our aim is to find a model with not many parameters, not less parameters, but just a nice combination of parameters, which will provide us with a nice fit to the data, plus a graph smooth enough, right, for our practical purposes. So that is our aim. So now what we will do is, we will try to figure out the maximum likelihood of this particular thing. And again, first we'll have to write its likelihood function. So we use the function as it is, and yeah, we ignore these constants that we have here. Don't really care that much about it, and just write it as constants. It's fine. And this is what you will have, and you multiply it again for all the ages. So here, this was only for one particular x. So here you will have it for all the ages. And once you do that, then again, so you will not have to carry these out, at least in theory. I don't know if you guys have this in R or not, but again, if it is, I think it's much straightforward. So what you will have to do here is just try to maximize this particular likelihood, and you will figure out the parameters values. So these are the number of parameters, and this is the number of times you will have to differentiate this thing, right? With respect to this, and ultimately with respect to alpha R plus S to figure out the values of each of these parameters simultaneously, which will allow you to observe whatever you have observed using this particular model to be the most likely one to be observed. So yes, and once you have these parameters, then all you need to do is just say your age, and you can get your value for this particular graduated rate. But again, how do we check whether this is indeed, a nice fit or not? So we have already seen techniques to figure that stuff out. But again, maximum likelihood estimation is not the only method that you can use. So another technique that you can use is to minimize the chi-square test statistic. So you can try to write observed minus expected upon expected. So here, this will be observed, and then you will subtract the expected. So observed will basically be dx, and this particularly will be expected. So this is what you expect from the model, right? If we assume them to follow Poisson, we expect this much. And that is again, that is what will come in the denominator again. And you try to minimize this particular chi-square test statistic, and you see what, and then you will just basically try to use. So here you are maximizing, here you will be minimizing. Again, equate to 0, but the double derivative should be greater than 0 instead of less than 0 if you're minimizing. Or else you can put a minus here in the test statistic, and you can try to maximize that, because maximizing minus of something is equivalent to minimizing that something, right? And this another technique that you can use is to actually minimize the value of the weighted least squares. So remember, whenever I put a graduated rate here, so these are my crude estimates, right, which I put a hat on, but here I have put in my graduated rate. So I conceive some formula for my graduated rates, and I expect it to be true, right? So now what I will do is, let's say if I have two formulas and I want to see which one of them fits the data better, I can use this particular kind of a technique, and I will see I'll take the one which minimizes this weighted least squares, right? So here the weights is actually tricky. So sometimes this is assumed to be inverse of the variance, because if you have a lower variance, then you have more confidence, right? So if you have more confidence, then you want to put more weight into that particular subtraction that you're doing at that particular age. So I think, yeah, that's there. But again, the weighing is based on the exposed to risk, which I think makes sense, because if you have more people being exposed to risk at some point in time, then that should hold more weight. So it's not that you, we do say that we should look at all the lives independently and in the same way. But again, we know that some of these lives, if you see some sort of a feature in some particular age range, then you should take that into account as well. So these weights will do that thing for us. But again, once we try to, let's say, maximize likelihood, minimize chi-square, or minimize this value of weighted least square, you will know which one of these models fits your data the best, right? But again, this is not where your work will end, because I think this is very manual and this is very technical in nature. But as an actuary, you will also have to see whether this data that you have fitted, whether the graph that you got, it adheres to the data very good. It gives you a very nice, it gives you the least whatever chi-square test or, everything else is perfect. But sometimes there are these basic general rules that we know are true in the data that we observe. So just to give you guys an example, here they have mentioned 3 of such cases. So the very first check you can do is, let's say if you're plotting the mortalities of males as well as females separately, we never plot them together, right? Because we want our data set to be homogeneous, and we do not expect the mortality rates of males and females to be, on the similar, they might project a similar pattern, but not the actual numbers, right? The actual numbers, we expect them to vary. But again, it is not any random variation that is observed. most often we expect the mortality of males to be higher than the mortality of females. And this is by nature. So these are some basic facts that people have generally observed. And again, these might change over the period of time. So it doesn't mean that this will always remain true, but we assume that this is what we expect to be at least there in whatever we plot, right? And the second thing here is, this is very interesting, right? Because what they're trying to say here is that the mortality of persons with life insurance policies is lower than that of the population as a whole. Do you guys want to guess why would this be the case? I mean, people who have taken the life insurance policies are less likely to die on an average than the whole population in general. Do you guys want to guess why could this be the case?
Is it because the people who are buying the life insurance policies may be economically more stable than the people who don't buy, so they have a good living, and that's why they are less exposed to risk? Like that.
Yes, that is indeed one reason. So it's like, so now in these chapters, in this chapter and the upcoming chapter, it all depends on how you reason. You state a valid reason, it's true. You do not state a valid reason, I mean, you state a valid reason against it, it's fine as well. As long as you state something which makes sense, then your answer will be correct. So there is no perfect or answer here. It's how you reason about the answer that you have chosen to choose. Okay, so here in this particular case, so this is again debatable, but generally what we see is that people who have life insurance policies are checked, they have undergone a thorough investigation of whether they are more likely to die or not. And if in the investigation, the insurance company finds out, okay, this person is already smoking a lot, that they already have a heart disease and blah, 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 so they're more likely to die, then they will not give that person an insurance, right? Because what's the point? It's just going to end up as a loss for the company. So we expect, on an average at least, that the people who have life insurance policies are less likely to die than the whole population, because the whole population consists of the people who have insurance and people who do not have insurance. So we expect people who do not have insurance, some people might also think it, as if, let's say, if a person does not have insurance, they do not expect to die, right? And that might be a reason why they do not tend to take the insurance. But again, we tend to see, and we tend to basically rely on what we observe in the majority of the cases and not pick out on one or two particular cases. So this is what is observed in majority of people, and that is why this is something that we expect our data to behave and show us. And the third thing that they're saying here is that the mortality of persons who have recently taken out life insurance is lower than that of persons who took out life insurance a long time ago. And again, I think this has a similar reasoning, because a person who has taken out a life insurance just now would have undergone a test recently. And if that is the case, then we know that they have a good chance of living than people who might have had a test, 10 years ago or 5 years ago. So on an average, this is what you observe. So again, whenever you adjust the rates and you see a graph, always at the end, you should make sure that this data makes sense. Because sometimes you never know what kind of error your data might contain previously. So even though you trust your techniques 100%, we shouldn't, put all of our senses into the models. They're models for a reason. If you wanted to model the real life, then my professor used to say, you should just look out of the window, because that is not what modeling is for. So we expect there to be some error, but some general characteristics we do not expect to miss out on. And these can be the ones, this can be deciding factors sometimes. So yeah, this is what you would have. And to check this, you can have a look at, previous investigations of the same population. So let's say if you're trying to study something about male and female population in India, you can have a look at the same study which would have been, let's say, done in some another country, developing country, sharing similar statistics with India, and see what was their result like. And again, I mean, do not bias yourself with that result because it could be different in India than that country. But if you expect something to be, I mean, I don't know how to explain this, but I guess it's all a judgment call, I guess. So sometimes you see that, yeah, I know for sure that this is what I will get as the end result. And if you do not, then you know that there is something wrong. And often otherwise you might also be sure that, okay, this is not going to give me the same result. And I know why is this not. So if you can justify why is it not the same, then I guess you have a reason, to go ahead with it and use that particular rate. So yeah, that is what they have included here. And yeah, so again, yeah, so this I guess we've already discussed. The financial risk that these people are talking about is just the risk of underestimating the mortality or overestimating the mortality. So if you underestimate, you are at a loss in case of a life insurance company, and if you are overestimating mortality, and then you are at a loss if you are into annuity business or pension business. So I think this is what you want to hedge against, and that is why you want your premiums to basically be, well defined. And again, there is this another factor of being competitive and not, because if you try to charge a higher premium, even though just to hedge against the risk that you think underlies, there might be some another company which will charge just a tad bit lower premium than yours and might try to, lure customers over their shop. So you don't want that to happen as well. So some trade-off exists always. Yeah. And here, when they're talking about changes in mortality, so this will study in much depth in the next chapter. So I'm just going to ignore. But again, this just says that basically not always you should, put all your eggs in one basket and assume that whatever has happened in the past will continue to happen as it is in the future. There are developments happening, and so just one example. Let's say if people were dying of SARS, flu, or something else in the previous year, or polio, let's say, but now we have a vaccine for it, right? So less people will be dying because of polio. So the mortality rate or the infant mortality rate, which was due to polio, will now not be as often as it was. So the trend will not continue once we have the vaccine. So I guess you should take those into account and not always rely just on the formulas and all that you see. And now here they have just discussed the graduation process in detail. So the very first thing that you do is you select a formula that you think might fit best to whatever data you observe. So it could either be just Gombots or Mayhem or a combination and a family, both of them. So here you have e raised to x square, and you can also have x cube and so on and so forth, depending on how flexible you want your model to be. Then you will have to determine the parameter values. So to determine parameter values, you can use weighted least square or MLA or anything else. So it's up to you. And once we have the graduated rates, then you will have to do a test to see whether it fits the original data, the crude data that you have well enough for our purposes. So I guess that is all about graduating your mortality rates using some particular formula. Any doubts with this? So again, this particular technique is not always helpful, and I think we'll just do it at the end for the three methods that we study. When are these helpful and when these are not the best ones to use? So I think let us move forward. So now sometimes what you see is you do not have much data. So let us say if you're trying to observe mortality rate of female non-smokers or female pensioners or something, so then you might have already prepared standard tables which you can rely on and bank on to basically, give you a graduated smooth rate, which might suit your purpose. So why go through the whole again, the whole technique of trying to find a formula and then fitting it again, because that is already been done for you. That is already been done for you in a standard table, right? So they've already fitted a formula and they already have produced rates. So sometimes you might see that you can do a graduation just by referring to a standard table. But again, you might not always see that there is a one-to-one nice relationship between the standard table and the crude rates that you observe. So all you will have to do is just plot your crude rates for the ages, and for the same ages, you plot your standard rates. And if you see there to be some sort of a difference, then you can try to identify if there is some pattern in that difference. And then we will try to figure out that pattern. So let me just show it to you guys. So sometimes all you will see is, let's say this is your crude rates and then this is your standard table. No, sorry. Yeah, so this is your graduated rates at the end, and this is what you observe in the standard table, right? So again, this is our end goal, and this is how we expect our graduated rates to be related to the rates that we observe in the standard tables. So the ones that we observe from standard table will have a S in the superscript. So you should always try to remember that. So again, you can sometimes see that there is a linear relationship, and oftentimes there will be a linear relationship. It is simple, and I guess this is one of the unique feature of using a standard table, is that this is very easy. You just have to do some plus or minus or addition and subtraction, and you are guaranteed a nice, smooth, and well adhered to the data graduated rates. So sometimes you can use this, and this is actually very unique. So what is happening here is that, this K could be positive or negative. It could be +1, -1, +2, -2, doesn't matter much. So you might observe that the crude rates that you have follow the same pattern as the ones in the standard table, but 2 steps. There is a lag of 2 steps, or there is a lag of -2. Maybe just for an example. So if you see that, then you might have some sort of a relationship like this, where if you want to figure out the graduated rate for age, let's say 26, then you will not use the standard table of 26 itself. You might see that the standard table rate for 24 suits well for 26. And this is not only for that one particular age, but also for the other X's. So this sort of pattern continues. And then you can basically use, these are just examples. You can try to fit other sort of relationships. Now the question will be, how do you figure out these relationships exist, right? So very simple thing we do in regression or in any, we plot the dots and we see if there is any relationship. And we try to get a line or something very nice. And once we have that, then yeah, that is what we will do. So, but even before we first figure out a link to the standard table with our rates, what we want to do is we want to select a standard table. And this is something which is very, very difficult sometimes. But again, if it is not difficult, then it is very easy, because sometimes you see that the data that you have, or the data that you want to figure out the graduated rates for, if let's say that does not correspond to any of the standard tables that you have, then there is no point, right? You cannot just approximate any standard table, because if you're using the rates of standard table to figure out your graduated rates, then you expect that the characteristics that your standard table possess are somewhat similar to the ones that you have, because then only it makes sense to use that particular standard table. So again, sometimes you have a standard table based on the whole population, which is the ones like PLT 15 for male or for female. Other times you also have standard tables for a particular class of lives. So when I'm talking about a particular class of lives, I mean, let's say for assured lives, you have a separate table. For pensioners, you have a separate table. For annuitants, you have a separate table. So you might have these sort of different tables. And if you see that you are working with the data similar to some table that you have, then the work is much easier, because all you have to do is figure out a link and you get your graduated rates, right? So I think that is, that is how you will use the standard table. But again, whenever we use, whenever we have a look at the standard table, not every time it is expected to be perfectly homogeneous in nature. And All we need is that the overall pattern of mortality, overall trend of mortality in the standard table should correspond to or should be somewhat similar to the crudes that we have observed, so that we can specify some sort of a smooth relationship. And again, I mean, why do we use standard table? Because one, we know that it is already smoothed out, right? They have already used a formula to figure out the values in the standard table. So we won't worry much about the smoothing of the data once we are trying to use the standard table. So in that way, you get one thing less that you want to worry about if you try to use standard table. But again, you know that because the data often is not much homogeneous, and this actually is not suitable if you have large set of data, because then I think you might find that I mean, a particular formula will not give you a good approximation throughout all the ages and all the kinds of people that you might have in that very large population that you observe. So this is most suitable when you have, like scanty data, very less data or not much of the data. So the step one is to figure out what standard table you want to use. Step two, you figure out a link between your standard table and the graduated rates. And once we do that, then you would want to figure out the parameter values. And again, how do you figure out the parameter values? It is using either maximum likelihood or weighted least squares or anything else that you deem seem fit. So you can use these and you will figure out the values of, let's say, A and beta in this, A and B in this case. And once we do that, so we have, let's say, observed some trends in the past and we know this, then all you need is X, right? So once you are given, let's say, age 70, you can look up the mu SX in standard table and use the A and beta that you have calculated to give you the graduated rate that you want to work with next. So step 3 is determining the parameter values. And again, here they are just talking about why weights based on the inverse of the estimated variance is a sensible choice. So this we have already discussed. What is this? Yeah, so I guess, this is the weight that they seem to use. So again, you see that it has exposed to risk in the numerator. So it is more for the lives where we have more people. It is more for the ages where we see more people. So I guess that's it. And then once we have established A, B's value, then what you want to do is just figure out the graduated rates. And you already know the function, you know the values from standard table, and all you need to do is plus minus calculator per tuck, and you get your answer for the graduated rates. And at the end, you would want to do some tests to see whether it approximates well or not. So again, as we have already discussed, you will not want to do a smoothness test if you are using a standard table, because we already know that it is, smooth automatically, right? Because, as long as you use a simple formula. So if you use a very complex formula, then it might not guarantee smoothness. But if you use a simple formula, then the smoothness that you see in the standard table is what you will expect in your graduated rates as well. So I think the only thing that you might want to check is whether it adheres to your data well or not. And again, the question might also arise, like, how do I figure out a simple function, right, which summarizes the relationship between the crude rates and the standard tables? So if there does not exist a simple relationship, then maybe this is not the best method to use. Because oftentimes, whenever this is the best method to use, you can easily see a relationship, and that will more often will just be a very simple one. So it will not be much complicated something. So this was all about the second technique that we can use to graduate our mortality rates. And that was one we saw we fitted a formula. And in the second, we saw that we used already existing standard table as a reference to figure out the smooth rates which align well to our crude rates, right? And now this is the third technique that we can use. So again, even before I introduce this technique, this is a bit weird, I guess. So let us just try to understand first what is happening here. So what we do here in this particular method, let us say this is the data that you observe, okay? So Okay, this is really not a good graph. Yeah, let us say this is the data that you observe, right? So now you want to fit some function to this particular graph, which is smooth enough and adheres well to the data as well, right? So if you try to use, let's say, some polynomial, then you might get something like this, So a polynomial doesn't guarantee that it will be smooth throughout these points as well. So what we want in essence is, so okay, if it do not fit a polynomial, so let's say if you don't use x square, x cube and stuff, if you only try to fit a linear model, then you will get these straight lines, right? You will basically get these straight lines. And again, this is very rough. This is not smooth enough for us. So sometimes you want to see an answer which is in between these two, not very bendy and curvy, but not linear as well. So you want something in between. So that is where this spline function comes into the picture. And what you do is you create some knots. So if you see that this differs from these particular points, you create these knots. And so again, these knots that I'm plotting, not necessarily they should be at equal space. There can be two edges that you're skipping through or some more that you're skipping through, it's fine. So we create these knots and then we try to approximate a function best to this knot. So instead of approximating a curve to the whole of these points, I only try to approximate a curve to these 2 points. Then to these two, then to these two, then to these two. But again, we want to ensure that the functions that we approximate in between these dots are smooth enough for our purposes, right? So I cannot have a function which approximates this particular relationship as, let's say, something like this. Okay, and for this particular curve, it goes something like this. So at this point, there is no same answer given to me by these two functions. So if I have something like this, let's say, and then if I get something like this is not what I want. This is not continuous in nature, right? So this is not something that I want, because I know for sure that when I am at this, I want only one and only one value for my estimate, be it the actual one or be it the other one. It doesn't matter, but I want a unique number, right? So sometimes you will see that you want to expect something like this, right? So maybe I should draw a curve or something like this here. But again, if you see here, this is continuous in nature. So here it wasn't continuous. This is continuous, but it is not continuous at this point. So whenever I'm talking about a function that I want to approximate to the data that I observe, I want my curve to be continuous at all the points. So now if I'm talking about, let's say, I should draw it better. So let's say if I'm talking about this particular graph here, I know that this is not continuous, right? So again, whenever I'm talking about continuity, I think you guys already, I don't know if you guys have studied this or not, but there is something known as left continuity and there is something known as right continuity. And you want those two answers. So let's say if you observe on x-axis that this is taking the value 1, then you will have limit some variable tending to 1 minus, and for the other one, you will have 1 plus. And the answers to both of these, 1 plus and 1 minus, should be the same for this particular function to be continuous at this point. And that is not the case when this meet orthogonally or a point and there is no curve. So what we look for is a curve something like this, where it is not only continuous here, but continuous here as well. Not only continuous here, but continuous through the bend as well. When they join together, it should be continuous there as well. So now this particular function is continuous throughout, right? So this is continuous throughout. And this would work well for our purposes. So this is how you decide what kind of a function you want. So again, we do not want a linear function and we do not want a very nice polynomial approximation. Even though it fits the data well, it might not be smooth enough for our purposes. So now what do we do? So that is where we use these spline functions. Name is a bit weird. But yeah, I think, it is sort of, don't try to be bogged down with the numbers and the formulas that you'll be seeing now. But the essence is what I have explained to you guys just now. And there is only like two more things that we want to add in those particular graphs if we are looking at the natural spline instead of the other splines. Okay, so the kind of spline that we will, so consider a spline as the curve through which we joined these two knots. So the points that I created, those are known as knots. And that is what we will be joining together to create a continuous line, a continuous function that will give us a graduated, that will give us our graduated rates. So here they're defining spline functions, and they say that these are polynomials of a specified degree. So when they're talking about a specified degree, if you approximate these functions, let's say as quadratic, then it will be a quadratic spline. If you use a cubic polynomial, which is let's say like x minus x j to the power of 3, which is what we will be using, is known as cubic spline. So I'll tell you guys, why do we not only look at quadratic? Why do we care about cubic spline much more than the other splines? So yeah, and there is certain continuity. No, we were at. Let me go again. So these are polynomials of a specified degree, which are defined on a piecewise basis. So when I'm talking about piecewise basis, it means from one knot to the another, right? So one piece, second piece are the pieces that you have in between the knots across the age range. The pieces join together at knots where certain continuity conditions for the functions themselves and their derivatives are required. So these continuity conditions we will see. So the very first thing that we have seen is that the function as a whole should be continuous, but we are yet to see about the derivatives, the conditions that we want the derivatives to hold. So again, we know what derivative measure is slope curvature or the rate of change of curvature, right? So we would want those derivatives to be 0. The first derivative should be 0. The second derivative should be 0 at the point that we are trying to figure out this particular thing. So again, here they have just said that this is actually one of the techniques that was used to figure out this ELT 17 in this particular years. And they used a linear combination of splines and a penalization term, which we'll discuss in the next chapter. So what is that penalization term, and why do we even have that sort of a term in this particular case? Okay, so now this is how your function would look like. So again, mu x is the mortality rate that we want to figure out at the end. And this is how we define our function that we think gives us our graduated rates. So again, you see that they don't have a circle up there yet, because we will try to see another approximation to this particular thing. And that is what we will be using. So as our estimate for the graduated rates. So again, here what we do is, let us say I have a particular, can you guys see my screen? I guess I'm back. Yeah. So what I was saying is that now, on the basis of the number of knots that you have, you will define these ages. So again, throughout all the ages that you observe, you can choose where all do you want your knots to be. And again, this is again on a judgment basis. So you can have more knots, you can have lesser number of knots, and we will discuss what happens if you have more number of knots. I guess you all can already guess, if you have more knots, then it might lead to undergraduation. And if you have lesser number of knots than required, then it might lead to overgraduation. So that is something in general that we observe. Yeah, but again, there's only one more condition that we require. So if I'm talking about cubic spline, all we have said is enough. We need the function to be continuous throughout, and the first derivative to be 0, second derivative to be 0 as well. But now if you're talking about natural cubic spline, which is what they have here. So when I'm talking about natural cubic spline, it isn't enough for me to just have a continuous function like this. I also need my function to be linear before my starting and after my end term. So it should be linear at ages below x1 and above xn. So this will be my x1 and this will be my xn. So it should be linear before this and after this. So if that is the case, then it is a natural cubic spline. Okay, so now enough talk about these splines. Let us get into the math. So there is no question as yet about splines in general. And that is why I think there is a good possibility that they might ask a question this time. So just don't discount this particular concept. And I think this is interesting. So yeah. So here what we try to do is, again, we will try to fit a cubic spline, and which is again a natural cubic spline. So we'll see why is it natural, because apart from this particular term that we will see what this is linear in x, right? So linear in age. So if this were, let's say, x squared, then before x1 we would not have a linear term. So then it wouldn't be a natural cubic spline. It would just be a cubic spline. So because we only have x here, it is an actual cubic spline. But again, let me just show this to you guys first. So this is how you define the function. And again, j goes from 1 to n. So n is the number of knots that you have, and j denotes the parameters. And again, here the function that you want to use is cubic. So you do is x minus xj raised to 3 here. So this x is what you know, and this xj will keep changing as in when your value of this particular j changes. So now if you evaluate your phi function at xj, what you will get is xj minus xj cube, right? Because if my x is equal to xj, then I use this formula. And xj minus xj raised to 3 is 0 itself. So that is what you have here. Now if you differentiate this particular function once, for 0, you will have 0. And for this guy, you will have 3 times x minus xj squared. And again, if you evaluate this thing at xj, you again get the value of 0 everywhere, right? Regardless of where you're looking at, what x you're looking at. Every value of x will give you the answer 0. Whenever you have x equal to xj, the derivative will be equal to 0, not everywhere. So only when your x is equal to xj. Let me just write this here. Only when your x is equal to xj. Okay. So this is the case. And now if you look at the third derivative, so the second derivative, you have 6 times x minus xj. So 3 times 2, 6, and this. So again, if you substitute xj, you will get a 0 here. And now if you try to differentiate it once more, you will get the value minus 6, which is not 0 anymore, right? So it doesn't tell you anything. So whenever we are looking at the rate of change of the curvature, we want it to be as minimum as possible. So ideally at the knots, we want it to be 0, right? And that is what we have up until this particular case. So that is why you look at a cubic function, and if you differentiate it once and twice, so if you differentiate this once, this will give you the slope. Differentiate twice, this will give you the curvature. So that is how you will ensure that it is actually smooth at the knots. You can try to check even further by using a power 4 equation, but that would just add on to something that might not also be necessary, and it costs us if we use a heavy demanding function as well. Okay, so now I'm going to so if I plot, let's say something like this, if I have these dots that I'm trying to approximate, so this, let's say x1, x2, x3, x4, and x5, right? So I can observe my age. So this is the line that I'm looking at. So my age can be below x1, right? So if my x is less than x1, then I know that all of my phi's are always going to be 0, right? Because my xj here, my j here is taking the value of 1, and my x is always less than x1. So this function takes a value of 0 everywhere. So this will be 0, and all you will be left with is this thing. So that is why your mortality rate for ages below x1 is just this, which is indeed a linear function of x. Now, for the cases for x in between x1 and x2, what do you have? You will observe some values, right? So now you will observe this particular values for x being greater than or equal to x1, right? So you're not only observing it for these, but for these as well. So now you can have some x's which take a value greater than x1. And for those cases, you will have x minus x1 cube. And that is where you will have this thing. So your phi 1 of x will be x minus x1 cube, and all the other cases will be 0 because you do not observe anything beyond this x2. So you only observe something in between here. So your spline function for the values of ages in between x1 and x2 will be this thing plus beta 1 x minus x1 to the cube. So this comes from the function that we have defined. This beta j times phi j, and this phi j is defined as this. And similarly, if you again try to do it for these cases, x2 and x3, you can easily see that you can have x greater than or equal to x1, you can have x greater than or equal to x2, and you can have x greater than or equal to x3. Can you have this? No, right? X is less than x3 for sure. So you have x1, x2, and that's it. For the rest of these, this will be 0, and the function that you get will look something like this. So once you have this, I erased everything. Yeah. So once you have this, and you can do the similar thing for all of the possible intervals that you see. And then for the last one, you see it will be, greater than this particular thing. So your x greater than xn. Now, what we assumed was that if we want to look at a natural cubic spline, we want our function to be linear before x1 and after x5, if this is the last one that we are looking at. But we observe that we get this big equation, right? It will start from 1 and it will go till k. If I'm assuming, it will go till n right here. So xn n. So we do this thing, and what you do is you try to combine these beta ones and you expand these equations in bracket. And what you will do is you will want the coefficients of x2 and x3 separately to be adding up to 0, because then only this function will be a linear in this particular term, right? So again, you do not have any x terms in here, but you have x square, x cube, and this is x. So you can still have this. This wouldn't be an issue, but all of the other stuff you shouldn't have. So what you do is you take all of the coefficients of x square. So here this is minus 3 beta 1 x1, minus 3 beta 1 x1, and so on and so forth. And you want the addition of all of these to be 0. And similarly, the coefficient of x3, which will just be beta 1 here and beta 2 plus up until beta n, this should also be 0. So if you have all of these two conditions satisfied and the functions defined in such a manner, then you are ensured to get a natural cubic spline. And this is a function that you define again, and you think might fit best to the data set that you have observed. And more often, this is actually a very good fit. So for this method, it doesn't matter if you have a small data set or if you have a large data set. As long as you can fit a good function, this is very good approximation because it is doing piecewise, right? It doesn't. So in the very first case, we looked at a formula, right? One formula only, and we were trying to fit it for all the ages. But here, if you see, the formula changes from one age interval to the another age interval. The formula does not remain same. So there is so much of flexibility that you can have if you are using this particular method. But again, not every time you want so much of flexibility, and this might just be, adding to the time cost and the other costs. So yeah, that's something that you want to have a look at as well. So now for linearity, we want this to be 0 and this to be 0 as well. Now what they are assuming, now if you try to use this particular condition and this particular condition and try to work out, you can actually come to a conclusion that your mu x is equal to alpha 0 plus alpha 1x and this thing. Now you might see that superficially this is same as the one that we saw earlier, but here you have a capital phi, which is defined as something else than previously. And now the summation only goes from 1 to n minus 2, not till n. So they have given a nice derivation of how did they derive this. Maybe I can just walk you guys through it, but it is actually very simple. So I think we have time, so we can maybe go through this. So yeah, so this is the formula that we started off with, right? So we will make use of these two conditions that we have derived. So the very first thing that they are saying is to subtract 1 from 3. So let us see what is our 1. 1 is this, 2 is this, and our 3 is what? Yeah, this is my 3. So this is my... Okay, so the very first thing that you do is you multiply 2 by xn, which was that all of your sums of beta should be 0. So if you multiply all of it by xn, you get something like this. And then you subtract this thing from 3. So the very first condition that you had was beta 1 x1, beta 2 x2, adding up to 0. You subtract it from this thing, and this is what you will get. And then you are just trying to rearrange this particular thing with beta n minus 1 on your LHS. And if you rearrange this thing, first you just put beta n minus 1 on the right hand side, and then you divide whatever coefficients you have throughout, and you get beta n minus 1 here. And now what you do is you rearrange your second equation for beta n. And this is the value that you get for your beta n. So beta n minus 1, this, beta n, this. And now you use this particular equation. So you start off with 4, and what you have is, instead of this beta n minus 1, you substitute this particular thing. So your beta n is equal to minus of all of these till beta n minus 2. And instead of beta n minus 2, you substituted this particular function. Okay, so this particular function, which can be summarized as this summation, you substitute it here. And once you get that, you just combine the coefficients of this beta 1 and this beta 1. So what you will have here is minus 1, so beta 1 minus 1 plus xn minus x1 upon xn minus xn minus 1. And if you do this additional subtraction, this is what you are bound to get. So this is what you will get, and you just multiply and subtract and all of this. So this is the answer that you will get, and which can be summarized as this thing. So this is nothing but just the value that you get for your beta n. So now you can write your beta n as this summation, where beta takes values from 1 to n minus 2. And this is what you have here. And now you start off with this particular thing, and what you do is you separate this up until n minus 2, and then you write beta n minus 1 times phi n minus 1 plus beta n times phi n. And blah, blah, blah. You substitute the value of beta n minus 1, and you substitute the value of beta n that you get. And this is what you derive at the end. So whatever this big thing that we have in the square brackets here, they denote it as capital pi here. So yeah, that is how you get this approximation, which only goes from 1 to n minus 2, not till n anymore. So this is the function that we have. And once we have the functions, and we can easily figure out the rates and do the thing. So the process is again similar, but here you will have to start by choosing how many knots do you want to use. So you can do trial and error, and you can see how many knots fit in the data the best, and blah, blah, blah. And you can decide, how many number of knots you should have, and at what position you should have the knots. So sometimes you might find it helpful to have more knots during the infancy and the childhood period, because that is the times when mortality changes quite often, and that is important changes, right? We do not want to miss out on those features of our population. But as and when they get older, it kind of follows a similar pattern. So you can have knots at more space than at younger ages. So that's not much. I mean, that's again, it's judgmental, and it's very subjective depending on the researcher. So once you decide how many knots you want and where do you want to place them, you calculate your functions. And once you calculate your functions, you can easily figure out you want to fit this particular equation to figure out the values of these parameters, so alpha 0, alpha 1, and beta j's. So you want to figure out the values of all of these parameters. And again, you can use the least square. So we know that this is the equation that we have fitted. So we will subtract this particular thing, and we will try to minimize this. And that will give us the value of the parameters. And once we get the value of parameters, you can easily get the values and calculate the graduated rates. And once we have that, we can do a simple test to check whether these adhere closely to the original data that we had or not, or whether this is smooth enough or not. So again, if you have more number of knots, the data is, the curve is less likely to be smoother. And if you have lesser number of knots, then it is less likely to adhere well to the data. So you have to find the right balance in there and just try to go with whatever you seem fits best. So here they have just given us two examples. So these dots are the crude rates, and this black line is the spline that you have drawn here, the function that we think fits best. So these red dots here are the knots that they have placed. So here, if you see, we have placed 6 knots. And again, so this curve is smooth in itself. But if you see, there is some higher infant mortality rate here, which is not captured by the data. Some sort of a higher mortality rate here, which again is not captured by this function. So this is not, and again here we are trying to underestimate. So this is not that well adherent to the data, right? It is smooth, yes, but it is not that well conforming to the data that we have. So maybe we can have more knots in here, maybe 1 knot here to fit a nice distribution here, fit a nice function over there. So that was for males. This is for females. Now, if you have a look at this, yes, there is some issue over here, but on an average, this seems like a good fit. So you still see some here and some things going on here, but it is not that significant, at least according to what they are mentioning here. So again, there are tests that you all are aware of, and we have studied in the previous chapters, that we can do to check these particular things and statistics. So this is just one example that they have given us to see how do we actually use the formula of this particular spline model. So again, here what they have done is, the question is, write down a formula for calculating the values of mortality at age X in the spline graduations illustrated in the graphs above in terms of the fitted parameters, the age X, and the functions capital Phi j, right? So this is what you will have. But again, if you see, we had 6 knots, right? So my n was 6. And when I'm using my capital Phi, my beta only goes up until n minus 2. So here you see it is capped at beta 4. You don't have beta 5 or beta 6. This is capped at beta 4. And again, we will just use the formula that we have defined earlier for this to rewrite this particular function. And we know the values of x1 and x5. So here I know my x1 is 0, x2 is 5, x3 is 15, and blah, blah, blah. So you can use these numbers to substitute in these values for this x5s and x1s and x6. And you can get this particular equation, which is for phi 1 in terms of these small phi's. And yeah, this is all you can do from the information that we have. So this was it about how do we graduate our mortality rates using splines. Any doubts with this method, guys? Anyone? Any doubts?
No, ma'am.
Mihir?
No, ma'am. No, ma'am.
Okay, good. So that's it. That is it about the 3 methods. So now here they have just compared all of these 3 different methods, and they're trying to say which one is good, which one is bad, in what situations. So the very first thing they're talking about is graduation by parametric formula. So again, you need to, so this is a very nice method because there is nothing subjective here. So you already have a specified formula. So again, there will be a choice that you as a researcher will have to make as to what formula you should use. But again, that might be dictated by the goodness of fit tests that you do at the end. So there is not much subjectivity here. And again, the only issue with this is that sometimes you might see that a single function might not give you a satisfactory fit for all the age ranges. So, or for all the age ranges, this might not fit very well. But again, sometimes if you use smaller number of parameters and if you, you can actually try to have a smooth graduation. And this approach is actually used quite often to produce standard tables. Because again, when you're trying to produce standard tables, you have large amount of data. And you cannot use already existing standard table to pair another, right? Because then, what would that be just? So you try to use the parametric formula to produce a standard table, which then can be used to figure out again the mortality rates for some another thing. But again, as we have already discussed, this doesn't suit well to all the ages. So you might see some accident, hump, and infant mortality, and all of these things, which matter a lot. So sometimes if you just have one particular function, then this might be problematic. So sometimes you can do is you can divide your age ranges and you can try to fit formulas, but then that would just be doing spline sort of something. So it's more or less similar. But again, here, even though you get a very good fit for the data with the formula that you have, when you try to extrapolate, so now when I'm trying to talk about extrapolation, I want to forecast something in future on the basis of what I have observed in the past, right? So if I'm trying to do something like this, then I have to be extra careful if I'm using a formula. Because sometimes if I try to use a specific formula, then it might not fit the ends very well. And when I'm trying to forecast, I use the end, right, to forecast what's going to happen next. So then that forecast would be way out of the line that we would expect it to be. So then that would be basically something to worry about. Okay, so now coming to the standard tables, this technique is used if you have small data sets, and the results are very good with those. And again, you should expect the characteristics of the standard table to be reflected in the ones that you graduate. So only use this method if you have experience similar to what you have a standard table for. But again, you can do some adjustments, and if it is not directly according to what you want, then you can do some further adjustments and so on and so forth. But again, this is like a very simple way to do this graduation. And yes, it is not suitable for preparing standard tables. So you should try to be wary of that. And it is not always easy to choose an appropriate standard table, because again, see, whenever we have standard table, we say that we expect them to be homogeneous, but it will not be perfectly homogeneous in nature. And again, it might not well sample, so the population that we have. So the ones that we want to figure out graduated rates for, and the standard tables that you might have available to you, they might not correspond to the same population. So let's say the geography is different. Let's say their sex is different. So maybe the standard table that you have is for females, and the population that you are looking at is for male. Or let us say they have it for combined, and you are looking at only males or only females. Then there is some issue, and you cannot basically decide what standard table to use or whether to use a standard table or not. So ideally, if there is much difference, then you should not use a standard table. And the third one is using spline functions. So again, if you have a small number of knots, then the graduation will be smooth. Yes, because the curves will be really nice. But again, it might not correspond well to the crude data that we have. So we might have to compensate something on that. So here, this can be used to produce standard tables. We have already seen an example. ELT something was produced using this spline technique. And yes, it is definitely not easy to choose how many knots you need and where should you place your knots. But again, that is more of a judgment. So if you see that there is more defined and expected variation in some age ranges, put more knots over there and put lesser knots over the other age ranges where you expect the curve to follow some similar pattern. So here again, you have to be careful about the extreme ages, because if you are trying to use the natural cubic spline, we have made an assumption. So it wasn't given to us that they were linear. We have made an assumption, and we have chosen some conditions to be satisfied for the parameters that we have, right, to make it a natural cubic spline. So that might sometimes not be up to the mark, and that might basically, hide some of the significant features of the data. So it might not be appropriate always to use that. And again, should be careful basically whenever you're talking about the extremes, because not always you will have a lot of data available at the extremes. So whatever you have fitted at the extremes is based on very, very small number of data, and basically the reliability of that then decreases as in when you have lesser number of data available. So yeah, here they have just said it, right? The spline method is a special case of graduation using a parametric formula, because you define so many intervals and you define different formulas for all of these intervals. So it's like doing it so many times using a parametric formula. So that's it. And this is a nice question. Maybe we should try this. So an actuary has conducted investigations into the mortality of the following classes of lives. A, the male members of a medium-sized pension scheme. And we want to graduate the crude rates and state with reasons an appropriate method of graduation for these classes of lives. So what do you guys think? If I'm looking at the male members of a medium-sized pension scheme, what kind of a technique do you guys think should be used here? Only 3 options, right? So I think it should be an easy guess. Not much to think about. What do you guys think?
If you have the standard table available with similar characteristics, then we can use that.
Yeah, right. Because I think this is like a very specific thing, right? We are looking at pension, we're looking at male members. So we might have a standard table available according to this. So actually, I mean, for pension people, there exists a separate standard table. I think it's called PA90 or something like that. So yeah, you can try to use that. So yeah, that's one answer. And for the B part, we have the female population of a large developed country. Now this can be tricky. So yeah, what kind of method do you want to use to graduate these rates? So we're looking at, a whole country, so a developed country, and all of its female population basically.
So for the whole country, as we have a large data, we can use parametric.
Exactly, right? So we have a whole country, so we have more number of data. So we should, of course, go with the parametric formula. And most often you will do such kind of analysis if you want to prepare a standardized table. And yes, we've already seen that parametric formula is very good. So you could use spline technique as well. But yeah, I mean, it depends on how you argue about it and all. So I think it's fine if you write spline as well in this case. So not much to worry. Oh, why is this pen not working? Yeah, working. All right. Okay, so here they have discussed the tests in brief, not all of the tests again. So basically all we need to know is that the thing that's going to change is the degrees of freedom, right? So if you're looking at the chi-square test, your degrees of freedom will change. So if you have, let's say, n number of ages that you're looking at, then you will want to subtract the number of parameters that you have estimated from this thing, if you are trying to use a parametric formula or something like that. So I guess that's all, and this is all repetition, I guess. So I think you guys can just go through this thing. The only thing important is this thing. So oftentimes whenever we use the chi-square statistic, we make sure that the observed data that we have and the expected data that we have do not come from the same population, because if it has, then there's not much point, right, of trying to figure out if our observed is, if it is close enough to the expected ones or not. So but that is not the case. So in our scenario, this does not hold, because our observed data is computed from the expected deaths that we observed. And the graduated rates are also from the deaths that we observe. But again, it is said that, yeah, it is still legitimate to use the chi-square test. So yeah, do not worry. No worries over there. At least from practical purposes, do not have to worry about that. But always remember, it will reduce some degrees of freedom. So you will just, if you are using a standard table, then yes, you will want to have a look at the formula that was fitted. And I think we've discussed a lot about degrees of freedom already in the previous chapter. So again, I mean, if you're using spline, then the number of parameters that you have, you will subtract those. So more often times you lose n degrees of freedom if you have n number of knots. Because why? Because this beta only goes till n minus 2, and the number of knots we have is 2 more, and these are the 2 parameters that it counts for, so it's fine. I mean, you have n parameters and n knots, so yeah, and that's something which is okay. This is something about cumulative deviations test, and they are just trying to aware you once again about the fact that if you get the summation, the test statistic for this test to be 0, then you should not use this test. So if you figure out the values of your parameters using MLE, then you will get the answer as 0. So you should not use this test in that scenario. Okay. Now this is something which is very, very interesting to me at least. So what happens if we have duplicate policies? Whenever we tried studying models in the previous chapter, we made an assumption, right? We made an assumption that one particular person has carried out only one policy. A person cannot have more than one policies in place. So, but what if a person has insurance not only, let's say, in HDFC, in LIC also, in ICICI also, right? A person has insurance in these 3 places and this person dies. So, if you're looking at the whole pool of data, if we are the CMI, the Central Authority for Investigation, then we see 3 deaths, right? We see 3 claims that we have to pay for. So we count them as 3 deaths. Why? Because the data that these CMI people keep is not of people specific. They keep data of policies. So it is very difficult for us to always keep checking, right, whether these policies correspond to the same person or not. So this is a huge task. So what is it that you can do if this is the case? And we know that this is usually the case. So here they are just saying that instead of observing persons and recording the number of persons that you have, exposed to risk, you only observe the number of policies that you have exposed to risk at a particular point in time. So this creates an issue because no longer those 3 claims that we observe are independent, right? They are dependent because if there is no claim on any of those, then there won't be any claim on either of those. And if there is a claim on any one of those, then there will be definitely a claim on all of those. So now these are no longer dependent policies, and these are no longer independent claims. So what happens is the variance increases. And now just to give you guys a very good example, I think I have an example of binomial case. So let us say I have a portfolio with 2 policies. Okay, so I have a portfolio with 2 policies, and A is the case where I have 2 independent lives. So here I'm looking at 2 independent lives, and B is the case where I have 2 policies held by the same life. So 2 policies held by the same life. So now from whatever these people have said to us, we expect the variance to be more for the case where we observe duplicates, right? So now let us say that I define my C as the number of claims that arise from a portfolio. So this denotes the number of claims arising, and my Q denotes the probability that a life claims. So this is just a probability that a life claims. Okay, so these are 2 variables that now I'm just defined. So now if I want to figure out the expectation, so expectation of C and the variance of C. Okay, in 2 cases, 1A and 2B. So I have these 2 policies. Okay, and let us do it for A guy first. So whenever I'm talking about, so okay, I'm again expecting this to follow binomial distribution. So I expect my policies to be binomially distributed. Okay, so now if you have a look at the expected number of claims, what will that be? That will just be 2 times Q. So it is N times P, right? NP. So N is 2 here, and P is what? Just Q. The probability that there will be a claim, right? So the expected number of claims that you think will arise is 2Q in A scenario. And for the variance, you will have 2Q times 1 minus Q, right? Because your C follows binomial with parameters 2 comma Q. So these are the parameters that you have. And now let us have a look at the another scenario. So in B case, what will be my expectation? So here I know that there is only one life, right? So my X follows binomial with 1 comma Q. I know there is only one life and there are 2 policies held by the same life. So my C here is 2X. Now if I want to figure out expectation of C, it will just be 2 times expectation of X, which is Q. So expectation remains the same, 2Q. But what happens to my variance? Variance will be what? This will come out as a square, right? So you will have 4 times Q times 1 minus Q. So you clearly see that there is a big difference, right? The variance has almost doubled in the case where we have duplicates. So sometimes what happens is you might know by how much does your variance vary if you have duplicates, but not every time you will know that particular case. So here that ratio is 2 because this divided by this is just going to give you 2, and that is known as the variance ratio. So once you know this variance ratio, then you can do something to compensate for this increased variance and allow it to not reflect in the graduated rates. But if you do not know, then you can't possibly do anything about it. And that is how you will try to figure out if in case you observe duplicate policies. But again, this is actually a very, very critical thing. And this is very common, I think, and they haven't justified with the kind of explanation that they have given here, at least. Because I don't know, maybe it's much more detailed and I don't know, that's it, I guess. So that was it about how can we try to see, the effect of duplicate policies. So there is no solution that they have presented to us here about what we can do if we even know the variance ratio. But we know that there is something we can do if at least we know the variance ratio. And if we do not know that, then just forget about it. Just assume that there is no duplicate policy, I guess. Yeah. So that's it for this particular chapter, I would say. And let me just close this. And oh no, maybe I should. Actually try to solve these practice questions. So here we just have to see whether these are true or false. Okay, so the very first statement is when graduating by reference to a standard table, you always need to test for smoothness. What do you guys think? True or false?
False.
Right? It is not always necessary because it's already smooth. Second, if the mortality of a whole population was recorded, there would be no need to graduate since random sampling errors would not have occurred. What do you guys think? Think about this.
Even if we have recorded for the whole large population, there will be some errors. So it is false.
Yeah, right? Exactly. So it's false. The third is graduating by reference to a standard table can produce good results even with scanty data.
Yeah, true.
Why do you think, Swapna, this is true?
We use standard table when we have scanty data, right?
Exactly, right? So, this is one of the features. I guess this is pretty clear. I think these are all theory questions. So, I guess, you all should just go through this on your own. If you have any doubts, just ask me about it. I guess that's it. Yeah. Just do it on your own. I would say just read through it. And so basically, more often it's just how you interpret. And if you can justify the reasoning, then every answer is correct. And if you're confused with any of your reasoning that does not match, let's say, with the ones that they have given in the answers, then you should confirm it with me once, and I can guide you much better. So I guess that's all from my side for today. And we will not have a lecture tomorrow. We will have a lecture day after, and that will be of the last chapter, chapter number 12. So I think that chapter is actually very interesting, because over there we will actually be forecasting the mortality rates, which is what and actually often has to do if you are into forecasting. So I guess that the chapter is very interesting, but it's sad to see that there were no questions asked from that chapter, at least till last 2 years. And because in 2019 there was one question, and that was also about advantages and disadvantages of one method. But again, I would say, I think, the chapter is interesting. So I'll see you guys on Tuesday, and the lecture won't be, early in the evening.